All right, going to go over the solutions to Worksheet I. What you see is a puck that's about to hit a stick in these four different scenarios, and depending on where the puck hits and if the rod is either connected to a pin that's keeping it fixed in place, or if it's just free to move, like cases B and C, we may see either just translational motion, just rotational motion, a mixture of translation and rotation, or neither. And so, kind of walking through each case. Case A is going to bounce on this stick, and we won't see any translation motion or rotational motion take place. Case B smacks into the stick and it's free to move, so we'll see both translation and rotation. In case C, we'll hit the dead middle of the stick, and so because it doesn't apply any torque, we'll just see translation. And then in case D, we'll hit the top of the stick, but it's fixed in place, so it won't move with translation, but it will rotate with rotation. And you can see in the table here the summary of the angular momentum, linear momentum, and kinetic energy for the puck rod system. This is of the whole system taking place, and they actually want us to treat it as both objects. I think for this entire worksheet, it's not going to split it up into just thinking about the rod or the puck, but having them both included. So, taking a look across, you can see that angular momentum is conserved in all cases. Angular momentum is always going to be conserved if you consider both the puck and the rod, because those are the two objects interacting. Linear momentum, though, is not conserved in case A and case D, because in those two instances with the pin sticking to the middle here, it prevents the rod from moving linearly, and so in those two cases, the puck will bounce off, and so it has some starting momentum this way, and it's going to go back the other direction with a different momentum, and the stick can't move to the right to conserve that momentum. That external torque by the pin is preventing that from being conserved. In the last one is ranking the kinetic energies. None of them have kinetic energy conserved because it sticks. Up in the top it says that the puck sticks to the rod, and because of that, then you're never going to have kinetic energy conserved. That's an inelastic collision. We learned an inelastic collision when things stick together, they warm up, and therefore we lose kinetic energy. All right, in part B, they want you to rank the most rightward linear momentum. And keep in mind, in the beginning situation, all of the pucks were moving to the right, but only a couple of those actually conserved linear momentum. So the ones that conserved all the linear momentum will have the most rightward momentum because it'll have all the amount of momentum that the system started with. And so that would be B and C. They perfectly conserve that linear momentum, therefore they will be equal in having the most rightward momentum. The pucks weren't traveling any faster than each other and they have the same mass, so therefore they're the same. Then ranking off of from there, when object D gets hit, object D is the one that was fixed by a pin and the ball was coming in like this. And so this ball will probably still travel to the right after it gets hit, and this will start rotating. So you lose a little bit of that rightward momentum. It's not perfectly conserved, but you still have some momentum to the right after that ball collides into this spinning object. So that's why D is the next in line. A doesn't conserve any because A, the ball hits right directly into the middle, and then the ball goes perfectly back to the left. So that's going to have the largest deflection back to the left by hitting the dead center, and there won't be anything moving to the right after the collision. All right, and then in part C, they want you to rank the most clockwise angular momentum. And keep in mind, angular momentum was conserved in all cases, but the amount of clockwise angular momentum is not the same in all cases. So for objects A and C, when that ball collided in the dead center of the pivot point, there was no ability to rotate the object at all, and so your total angular momentum for those cases before impact was zero, and it's conserved. The total momentum after is still zero, but that's why they would have the least clockwise angular momentum, because it started at zero and stays at zero. And that then is less than these other two situations, B and D, where the ball hits and is able to spin the object and make them rotate clockwise. And by rotating clockwise, those two are equally rotating in the way that they get hit, and therefore they have the most angular momentum. And that's going to do it for Worksheet I. If you have any further questions, please come find me when you get back to class, and we can go through it in more detail. Thanks. Have a great day.